My name is Chrysoula Aza, and today I'm going to talk my current work about trusses of nonlinear morphing elements, supervised by Alberto Pereira and Mark Seng. So, a quick look on what's on the menu today. So, I will introduce you to the concept of my research, then I'll go through some results, and we'll leave you with the conclusions and our thoughts and plans for the future. So, my research lies in the broad area of compliant mechanisms. Here I will focus on multi-stable ones. So, current compliant mechanisms rely on flexible members and their elastic deformations in order to transfer motion, force, or energy rather than the mobility of joints. But this may offer, although this may offer the ability to achieve multi-stability, it may result in the development of high stresses in these components, and thus this poses limitations to the design configurations. To address this issue, a compliant mechanism that uses morphing composite structures as the flexible elements is introduced. These elements are able to change shape and undergo less deformations while maintaining their structural integrity. Specifically, the morphing elements used in the compliant mechanism are composed of carbon fibers assembled in a double helix architecture. These helical elements can deform from an extended to a fully coiled configuration similar to springs, but they exhibit the nonlinear stiffness characteristics that can be tailored. So, for the study of the compliant mechanism, we focus on a simple truss structure, modified von Mises truss, pinjoided at the apex and base supports. For the analysis of the mechanism, we use two approaches. First, an energy approach to identify potential stable and unstable configurations. And then, given the nonlinear nature of the system, a path-following method is used to obtain potential load paths that connect the stable states. So here are the results for double helices assembled in strip trusses for different layups. Only symmetric layups are considered here. As we can see, the energy landscapes are quite different between different layups. And we can see that for a layup with all plies at 0, the structure is bistable. You can see here, so the stable points are the initial configuration and the symmetric one. And for a ply angle between 0 and 90, you can focus on the second one, and you can see that we have 4 stable states in this one. The initial, the bottom, and 2 when the spring the double helices are collinear. And for a 0 ply at the 90s, the mechanism is monostable with only 1 when the springs are collinear. But in this case, we have 4 binary equilibrium. Now, looking at the load displacement graph when we apply a vertical load to the system, we can see that the apex, we have a bifurcation, and with the apex can have a horizontal and vertical displacement. And we can see that all the stable and unstable states are connected through this path just by applying a vertical load. So next, we have different trusses, initial truss angle. So we can see that in solid truss, the mechanism is bistable compared to the 4 stables we seen previously in a stiff truss. But in both cases, we get the bifurcation and all the points are connected. So to sum up, we can see that just by changing the layup of the strips in the double helices or the initial truss geometry, we get different mechanism behavior. And also that just by applying a vertical load, the equilibrium path bifurcates, so enable all the states to be traversed. So as for the future, I'm going to focus to explore the reconfigurability of the mechanism. It's something that I'm already working on, and to manufacture and test a prototype so we can validate our results. So that was all from me. Thank you for listening. If you have any questions,